Our galaxy contains more stars than grains of sand on every beach on Earth combined. It spans a distance so vast that light, traveling at 300,000 kilometers per second, would take 200,000 years to cross it from one side to the other. And yet, from the surface of our planet, the entire structure appears as nothing more than a faint smear of light stretched across the night sky, a pale road that ancient peoples interpreted as milk spilled by gods, as a path walked by the dead, as a river in the sky with no source and no end. The truth, when science finally caught up with it, turned out to be more extraordinary than any myth. The Milky Way is a barred spiral galaxy, a colossal, slowly rotating pinwheel of matter, light and invisible mass. At its heart burns a monster along its arms. New suns ignite from cold gas every year. At its edges, ancient stars drift in the dark older than Earth by billions of years. And threading through all of it, making up the vast majority of its total mass, is something we cannot see, cannot touch, and cannot yet fully explain. Today we will travel across this structure. We will leave the solar system behind, move through our galactic neighborhood, visit some of the strangest worlds ever discovered, approach objects so extreme they redefine the meaning of the word matter, and finally pull back far enough to see the Milky Way for what it truly is, one of the most complex and beautiful structures in the known universe. We begin where all journeys begin, close to home. For most of human history, the stars appeared fixed and permanent, scattered across the sky in patterns that never changed from one generation to the next. The universe seemed static, eternal, unchanging. We now know this impression was simply a product of our short lifetimes. Stars move. Stars drift. The nearest ones move fast enough that, over centuries, their positions in the sky shift measurably. And the very nearest of all, a faint red point of light invisible to the naked eye, is creeping toward us even now. Proxima Centauri sits 4.25 light years from the Sun. That number sounds small in galactic terms, but it represents roughly 40 trillion kilometers of empty space. No spacecraft ever built by human hands has traveled further than the outer edge of our own solar system. The distance to Proxima Centauri is approximately 7,000 times greater. And yet, by cosmic standards, this star is our immediate neighbor. It belongs to a triple star system called Alpha Centauri, 3 stars bound together by gravity, each following its own path around their shared center of mass. The 2 larger members of this family, known as Alpha Centauri AA and Alpha Centauri B, form a close pair separated by a distance that varies between roughly 11 and 35 astronomical units as they trace their elongated orbit. One complete circuit takes approximately 80 years. Alpha Centauri A is the dominant partner, a star very similar to our Sun, slightly larger and slightly more massive, emitting about 1.5 times as much energy. From Earth, at a distance of 4.36 light years, the 2 stars appear as a single bright point, the third brightest object in the night sky, though invisible from most of the northern hemisphere. Alpha Centauri A has been examined closely for signs of planetary companions in 2021. Observations made in the infrared suggested the possible presence of a planet-like object near the star. If confirmed, this object would have a mass somewhere between 9 and 35 times that of Earth, a radius between 3 and 7 times larger than our planet, and an orbital period of roughly 1 year at a distance of about 1.1 astronomical units from its star. These figures remain unverified. The data may reflect a real world circling our nearest stellar neighbor, or it may reflect an artifact of measurement. Further observations with advanced instruments, including the James Webb Space Telescope, will eventually provide a clearer answer. Alpha Centauri B, The smaller of the two main components is an orange dwarf. Its mass is about 90% of the Sun's, its radius roughly 86%, and its surface temperature slightly lower, around 5260 Kelvin. The difference in temperature gives it a warmer, more orange color compared to the yellowish white of our own star. Its total luminosity is about half that of the Sun. What makes Alpha Centauri b stand out is its activity. The star is notably energetic in X-ray emissions, and its surface shows regular flares and ejections of stellar material. This behavior would have significant implications for any planet orbiting close to it, since the stream of high-energy particles from such events could gradually erode a world's atmosphere. No confirmed planet has been found around Alpha Centauri b. A detection announced in 2012 briefly suggested the presence of a small rocky world with an orbital period of about 12 days. But the finding was retracted 3 years later when researchers identified an error in how the data had been processed. The correction was a reminder of how difficult it is to find Earth-sized planets around other stars. The signals are vanishingly small, and the margin for error is slim. The third member of the system tells a very different story. Proxima Centauri is a red dwarf, a class of star that outnumbers every other type in the galaxy by a significant margin. Its mass is only 12% of the Sun's. Its radius is about 7 times smaller. Its surface temperature barely exceeds 3000 Kelvin, and it emits just 0.17% of the energy our star produces. If Proxima were placed where the Sun now stands, it would be barely visible in Earth's daytime sky. Despite this dimness, Proxima holds 2 confirmed exoplanets and remains one of the most closely studied objects in astronomy. The first planet, designated Proxima Centauri b, was detected in 2016 using the radial velocity method and confirmed by spectroscopic observation 4 years later. It orbits at a distance of 0.05 astronomical units, so close that a year on this world lasts just 11 Earth days. Its mass is estimated at 10 to 20% greater than Earth's, and its radius is about 1.3 times our planet's. The planet sits within Proxima Centauri's habitable zone, where liquid water could theoretically exist on the surface. Though the question of whether this is actually possible is complicated by the star's intense flare activity and by the fact that the planet is almost certainly tidally locked, meaning one side faces the star permanently while the other faces the permanent dark of space, a tidally locked world is not automatically uninhabitable. A thick atmosphere could, in principle, redistribute heat from the day side to the night side, keeping temperatures within survivable bounds across a wider area. But Proxima Centauri regularly bombards its surroundings with ionizing radiation without a strong magnetic field, and there is currently no evidence that Proxima b possesses one that radiation would steadily strip away any atmosphere the planet might have. The question of whether Proxima Centauri b is barren rock, frozen wasteland, or something more interesting may not be answered for decades. The second confirmed planet, Proxima Centauri c, orbits much farther out, about 1.5 astronomical units from the star, completing one orbit every 5 years. Its mass is estimated at 6 to 8 times that of Earth. Its temperature is accordingly frigid, around 39 Kelvin, or more than 200 degrees below 0 Celsius. At this distance from such a dim star, the surface receives almost no useful energy at all. Observations have suggested this planet may possess a ring system with a radius roughly 5 times that of Jupiter, though this remains to be confirmed. Whether Proxima c is a mini-Neptune or a super-Earth depends on its size, which has not yet been precisely measured. A third, much smaller candidate has also been proposed in more recent data, a world with perhaps a quarter of Earth's mass, orbiting even closer to the star than Proxima b, with a surface temperature around 87 degrees Celsius. As with many boundary-pushing detections, this one requires independent confirmation before it can be accepted as real. The Alpha Centauri system has been receiving Earth's radio transmissions for over a century. Those signals, leakage from our radio and TV's broadcasts, have long since passed through interstellar space and washed across whatever planets orbit those distant suns. Whether anyone or anything has noticed remains unknown. The 40 trillion kilometers separating us from our nearest neighbor remain uncrossable with any technology currently in existence. Even the fastest probes ever launched from Earth would need tens of thousands of years to make the journey. There is, however, a serious proposal on the table. The Breakthrough Starshot initiative envisions sending a swarm of miniature probes, centimeter-scale craft equipped with ultra-thin reflective sails, toward the Alpha Centauri system within the coming decades. These probes would be accelerated by a powerful ground-based laser array, potentially reaching speeds approaching 20% of the speed of light. Another 4 years would pass before any data collected by the probes could travel back to Earth. The engineering challenges are formidable, but the concept is physically sound. Within the lifetimes of people alive today, the first close-up images of another star system may become a reality. 6 light-years from the Sun, slightly further than Alpha Centauri, a small red star drifts through space at high speed. Its official designation is GJ699, though it is more commonly known by the name attached to it over a century ago, Barnard's star. What makes Barnard's star remarkable, besides its proximity, is its motion. It moves across the sky faster than any other star as seen from Earth. Over the course of 180 years, it would traverse a distance in the sky equal to the apparent diameter of the Moon. This rapid motion is partly a result of its closeness and partly because the star is genuinely moving fast. Approaching our solar system at more than 100 kilometers per second. In approximately 10,000 years, Barnard's star will be the closest star to our Sun at a distance of only 3.8 light-years. Despite this approach, Barnard's star will never be visible to the naked eye. Its mass is only 17% of the Sun's, its radius 6 times smaller, and its surface temperature hovers just above 3,100 Kelvin. The star emits roughly 2,300 times less energy than the Sun. It is intrinsically one of the faintest stars in our neighborhood, visible only through a telescope. In 2018, the results of a 20-year observational campaign were published, suggesting the possible existence of a planet orbiting Barnard's star. This candidate world, designated GJ699b, would be a cold super-Earth with a mass at least 3.2 times that of our planet, following a 233-day orbit at a distance of about 0.4 astronomical units. The orbital path does not cross between the star and Earth, which makes direct atmospheric analysis impossible. Instead, researchers rely on mathematical modeling to infer what conditions might be like there. The conclusions are not encouraging for life as we know it. The planet receives about 50 times less energy from its star than Earth receives from the Sun. The calculated surface temperature is approximately 105 Kelvin, more than 160 degrees below 0 Celsius. The surface, if one can be called that, would be locked under a deep layer of ice and frozen gases. And yet even here possibilities exist. Tidal forces generated by the gravitational interaction between star and planet can generate heat deep within a world's interior, a process seen in our own solar system on bodies like Io and Europa. Radioactive decay of heavy elements in the planet's core could contribute additional warmth. If these combined effects are strong enough, a subsurface ocean could exist beneath the ice, isolated from the stars, insulated by kilometers of frozen material, but possibly warm enough to sustain some form of chemistry. Whether that chemistry could ever rise to the level of biology is a question that current science cannot answer. Barnard's star adds another reason to be interested: its age. At over 10 billion years old, it is among the most ancient stars in our stellar neighborhood. If life did find a foothold in those lightless depths, it would have had an extraordinary amount of time to develop and diversify. The star will burn slowly for trillions of years to come. Whatever is happening in the dark beneath those ice sheets has barely begun. In the opposite direction from Barnard's star, at a distance of 8.6 light-years, lies one of the most recognizable objects in the entire night sky. Sirius, the brightest star as seen from Earth, outshining everything except the Sun, the Moon, Venus, and Jupiter at their brightest. Sirius is not the same object from close up as it appears from Earth. What looks like a single point of blazing white light is actually two stars orbiting each other, currently near the maximum of their separation at around 30 astronomical units. The dominant star, Sirius A, is a blue-white main sequence star approximately twice as massive as the Sun, 70% larger in diameter, and radiating 25 times more energy. Its surface temperature reaches approximately 10,000 Kelvin. Standing on a hypothetical planet at Earth's distance from Sirius A, the sky would be filled with a blue-white sun of almost unimaginable intensity. The second component, Sirius B, appears faint beside its brilliant companion. But it is one of the most studied objects of its class. Sirius B is a white dwarf, the dense, dead remnant of a star that once burned far larger and hotter than Sirius A itself. Its current radius is only about 6,000 kilometers, slightly smaller than Earth, yet its mass is nearly equal to that of the Sun. The resulting density is extraordinary. A teaspoon of its material would weigh several tons. Despite no longer generating energy through nuclear fusion, Sirius B radiates intensely at a surface temperature of around 25,000 Kelvin, white hot from the residual energy of its long collapse. Sirius B provides a window into the future of many stars, including our own Sun. The white dwarf is what remains after a star like the Sun exhausts its nuclear fuel, expands into a red giant, sheds its outer layers as a planetary nebula, and leaves behind a dense, slowly cooling ember. In this sense, looking at Sirius B is looking at the eventual fate of our solar system's central star. Though that fate lies roughly 5 billion years away, Sirius B carries another lesson beyond its physical properties. Its very existence in this binary system required scientists over the course of the 19th and early 20th centuries to fundamentally revise their understanding of the possible end states of stars. When its unusual properties were first being characterized, a star of roughly solar mass compressed into the size of a planet. The physical mechanisms responsible were not yet understood. Only the development of quantum mechanics in the 1920s and 1930s provided the theoretical framework needed to explain how electron degeneracy pressure could support such an object against further gravitational collapse. Each stage in understanding Sirius B forced a deeper engagement with the most fundamental physics of matter and gravity. In this sense, the second brightest star in the sky is not merely a beautiful object in the night. It is a document written in light, recording the processes by which the universe manages its stellar material. No planets have been confirmed around either component of the Sirius system. The orbital dynamics of a tight binary make stable planetary orbits more difficult to maintain over long timescales, particularly in the range of distances where liquid water could exist on a planetary surface. Any worlds that may have orbited the progenitor star of Sirius B would have experienced catastrophic conditions during its red giant expansion and would likely not have survived. The Sirius system, for all its brightness, is probably a largely empty place, two extreme stars circling each other in a void. Between Sirius and the Sun, and scattered across the broader stellar neighborhood within 15 light-years of Earth, approximately 50 additional star systems are known. Some of these are single stars like our Sun. Others are binary or multiple systems. A small number have confirmed planetary companions. Together with Alpha Centauri, Barnard's star, and Sirius, they form the local galactic community, a sparse and scattered collection of stellar objects separated from one another by light years of cold, dark vacuum. Most of these nearby stars are red dwarfs. The statistics of stellar populations make this inevitable. Red dwarfs outnumber all other stellar types combined by a ratio of several to 1. They burn slowly, they live almost forever by cosmic standards, and they are the most likely home for any planets in the galaxy's stellar census. Whether any of them harbor life is a question that science is only now acquiring the tools to seriously investigate. 42 light years from the Sun, in the constellation Ophiuchus, lies a star so dim and so red that it can only be detected through a telescope. Gliese 1214, a red dwarf with roughly 30% of the Sun's mass. Stars of this class are the most common type in the galaxy. They are also the longest lived, burning their limited fuel reserves so slowly that the smallest of them will remain on the main sequence for longer than the current age of the universe. For planets, a red dwarf host brings both advantages: extreme stability over immense timescales and severe challenges, including chronic flare activity and tidal locking. Around Gliese 1214 orbits one of the most thoroughly studied small exoplanets in the galaxy's catalogue. Gliese 1214b, a world whose interior is thought to be dominated almost entirely by water. The evidence for this interpretation lies in the planet's measured density. Its mass is approximately 6 times that of Earth, and its radius is about 2.7 times as large. These two figures combined give a density of roughly 2 grams per cubic centimeter, far below what would be expected from a world composed mainly of rock and iron, and consistent instead with a composition that is 3/4 water and 1/4 rocky material. The word water, however, covers only part of the story. The conditions on Gliese 1214b are nothing like the oceans of Earth. The planet orbits just 2 million kilometers from its star, about 75 times closer than Earth orbits the Sun. This orbital radius is so small that one full circuit takes only 36 hours. The planet is tidally locked, showing the same face to its star at all times. The surface temperature on the illuminated side is estimated at somewhere between 393 and 593 Kelvin, between 120 and 280 degrees Celsius, depending on assumptions about the reflectivity of the surface. At these temperatures and the atmospheric pressures implied by the planet's mass, water does not behave in any way familiar from everyday experience. The lower atmosphere would be filled with superheated steam at pressures exceeding 15 times Earth's atmospheric pressure at sea level. The boundary between ocean and atmosphere would be blurred, steam above, boiling liquid below, the two states shading into each other without a sharp transition. Going deeper, the pressure continues to rise. At a depth of approximately 100 kilometers, the pressure and temperature together push water into an exotic crystalline state, a form of ice denser and harder than any natural ice found on Earth, stable at extremely high temperatures that would melt ordinary ice instantly. This layer of exotic ice could extend 5,000 kilometers deep, covering what remains of the planet's rocky core. Beneath the ice, the rocky core itself, probably composed of silicate minerals and metals, would be subjected to pressures extreme enough to alter its mineral structure beyond recognition. The entire planet is an object that shares the name Ocean World with places like Europa in our own solar system, but is physically almost unrelated. Spectroscopic investigation of Gliese 12.12's atmosphere has been attempted using the transit method, in which the slight dimming of the star's light as the planet crosses in front of it carries imprints of atmospheric absorption. The results have been frustratingly ambiguous. No clear signatures of hydrogen, helium, water vapor, or other expected molecules have been firmly detected. The leading explanation is that high cloud decks in the upper atmosphere, possibly composed of mineral aerosols or heavy water vapor droplets, are obscuring the spectral signal from the atmospheric layers below. The true composition of the atmosphere remains hidden. For life, ocean planets of this type present formidable obstacles. The trace elements and minerals that biochemistry requires, phosphorus, sulfur, iron, and dozens of others, must be available in the water in usable forms. On Earth, much of this chemical complexity arises from the interaction of ocean water with volcanic rock at the seafloor, a process that continuously introduces dissolved minerals into the ocean. On Gliese 1214b, the seafloor is not rock but high-pressure ice. Chemical exchange between the water and the rocky interior is possible only in narrow zones at extreme depth, and whether the products of that exchange can reach habitable pressure and temperature conditions is deeply uncertain. Nevertheless, ocean planets appear to be common. NASA's modeling work, published in 2020, estimates that billions of such worlds exist in the galaxy, some cold, maintaining their oceans under an insulating ice shell, and some warm and steaming like Gliese 1014b. Water is among the most abundant complex chemical molecules in the universe, produced abundantly in dying stars and distributed through interstellar space by nova explosions and stellar winds. Wherever the physical conditions allow it to accumulate, it does, and wherever it accumulates in large quantities, the question of chemistry and eventually biology is not unreasonable to ask. 340 light-years from the Sun, past dozens of other stellar neighborhoods, each with their own particular character, lies a star that would simply swallow the concept of scale most of us carry around in our heads. CW Leonis, also catalogued as IRC plus 10^6, is a red giant in the final stages of its life. And in terms of sheer physical size, it is one of the largest known objects in the local galaxy. At the peak of its pulsation cycle, the radius of CW Leonis reaches approximately 560 times that of the Sun. To put that in perspective, if this star were placed at the center of our solar system, its surface would extend more than halfway to the orbit of Mars. Mercury, Venus, Earth, and Mars would all be submerged within the star's outer atmosphere. Even the inner edge of the asteroid belt might brush against those tenuous, scorching layers. This physical immensity is not matched by the star's mass. CW Leonis is thought to have begun its life as a blue-white star between 1.5 and 4 solar masses, a relatively modest progenitor. What has made it so large is age and process. Over billions of years, the star has consumed its hydrogen fuel and transitioned to helium burning in its core. The outer layers have expanded dramatically in response to the changing pressure balance within the star, puffing outward into a structure of enormous but low density extent. The star is now unstable. Its luminosity varies over a pulsation cycle of about 649 days, swinging between roughly 6,250 and 11,300 times the Sun's total energy output. At its peak, CW Leonis is one of the brightest stars in the infrared sky, despite being invisible to the naked eye due to the thick cocoon of gas and dust that surrounds it. That cocoon is one of CW Leonis' most scientifically fascinating features. As the outer stellar layers become more rarefied and loosely bound, the star sheds material into surrounding space at a prodigious rate, losing roughly 7 Earth masses of material per year. Over the 69,000 years the nebula has been building. This has produced an expanding cloud with a mass about 1.5 times that of the Sun and a diameter extending to 84,000 astronomical units. Within this cloud, astronomers have detected approximately 70 distinct chemical compounds, including carbon dioxide, water vapor, ammonia, methanol, and a range of heavier elements extending partway up the periodic table. The water content was particularly surprising. Standard models of stellar evolution predicted that oxygen in the outer layers of a carbon-rich star like CW Leonis would be entirely consumed in forming carbon monoxide, leaving no free oxygen available to combine with hydrogen and produce water. The detection of abundant water vapor challenged this prediction significantly. The best current explanation involves gaps or transparent patches in the outer stellar layers where ultraviolet radiation, likely generated by the star's own magnetic activity, breaks apart silicon oxide and carbon molecules, liberating oxygen atoms that then react with hydrogen. But the precise mechanism remains an active area of investigation. In 10 to 30,000 years, CW Leonis will exhaust its remaining fuel entirely. The outer layers will be ejected in a final expansion, leaving behind a white dwarf of about 0.8 solar masses, hot, dense, and cooling slowly for the next several billion years. The expanding shell of ejected material will light up as a planetary nebula, briefly making the dead star one of the brightest objects in its region of the galaxy before the gas dissipates and darkness closes in again. The shockwave and extreme temperatures of that final event will forge new heavy elements, uranium, gold, lead, that were never present inside the star. These atoms will seed the next generation of interstellar gas clouds, where they may eventually find their way into the bodies of new planets, new oceans, and perhaps new forms of chemistry we have not yet imagined. Not all extreme planets are cold. Some exist in conditions of such violent heat that the very concept of solid ground becomes meaningless. Around an orange dwarf star 202 light-years away, a world known as K2-141b demonstrates what happens when a rocky planet orbits too close to its sun. The star K2-141 is somewhat smaller and cooler than our own, about 70% of the sun's mass and radius, with a surface temperature near 4,600 Kelvin. The planet that orbits it does so at a distance of only 0.007 astronomical units, roughly 2 million kilometers, 75 times closer than Earth is to the Sun. One full orbit takes about 6.5 hours. The planet is tidally locked, meaning the same face always points toward the star. K2-141b is 5 times as massive as Earth, with a radius 1.5 times as large. Gravity on its surface is at least twice as strong as on our planet. Estimates suggest that its dense metallic core makes up between 20 and 50% of its total mass. The temperature on the day side exceeds 3,270 Kelvin, nearly 3,000 degrees Celsius. At these temperatures, most rock and metal do not simply melt, they evaporate. The surface of the day side is thought to be covered by an ocean of lava, perpetually boiling, its surface continuously evaporating into a heavy, dense atmosphere composed largely of vaporized minerals, metallic oxides, and silicate gases. The atmospheric pressure at the surface of this vapor envelope is estimated to be at least 15 times higher than Earth's atmospheric pressure at sea level. Meanwhile, the night side of K2-141b is a different world entirely. Far from the star, stripped of the volcanic warmth of the day side, the temperature plunges far below freezing. The temperature gradient between the two hemispheres drives winds of extraordinary speed. Approximately 1.75 kilometers per second, more than 5 times the speed of sound at sea level on Earth. The noise generated by these winds, if a human ear could somehow survive long enough to detect it, would be continuous, overwhelming, and unlike anything in our experience. The cycle of evaporation and condensation on K2-141b has a strange completeness to it. Metallic vapors rise from the dayside ocean, are swept by high-altitude winds toward the night side, cool and condense into a kind of liquid metal rain, and then flow in rivers back toward the magma ocean on the day side. It is a hydrological cycle of sorts, running not on water but on molten rock and vaporized metal. Even K241b, extreme as it is, does not hold the record for heat among known exoplanets. That distinction belongs, at time of writing, to a world 670 light-years away called Kelt 9b. This planet orbits a massive blue-white star of about 2.6 solar masses, at a distance of only 0.035 astronomical units. One orbit takes just 36 hours. Kelt 9b is a hot Jupiter, a gas giant with 2.8 times the mass of Jupiter and approximately twice its radius. Its surface temperature is measured at around 4,600 Kelvin, making it hotter than many red dwarf stars. In the depths of its upper atmosphere, where the extreme heat causes metals to ionize, temperatures may reach 11,000 Kelvin or higher. Under these conditions, iron and titanium exist not as solids or liquids but as ionized gases, swirling in the turbulent atmospheric layers alongside hydrogen and helium. The stellar wind from Kelt 9 continuously strips material from this bloated, overheated atmosphere. By one estimate, the planet loses the equivalent of 68 Earth masses of atmospheric material every billion years. Eventually, assuming the host star does not consume it first by expanding at the end of its life, Kelt 9b could be stripped of its entire gas envelope and left as a dense, bare, rocky core. Whether this will happen before the star expands and engulfs the planet remains an open question. Some planets survive encounters with their dying stars that by rights should have destroyed them. One such world lies 4,570 light-years away, orbiting a star designated V391 Pegasi. Today, V391 Pegasi is a white dwarf, about half the Sun's mass, roughly a quarter its size, and heated to a surface temperature of nearly 30,000 Kelvin. All nuclear burning in its core ceased long ago. Ahead of it lies nothing but an endless cooling, eventually arriving at the theoretical endpoint of stellar evolution, the black dwarf, an object so cold it emits no detectable light at all. The planet orbiting this remnant star, V391 Pegasi b, is estimated to be about 3 times as massive as Jupiter. Its orbit currently passes 1.7 astronomical units from the stellar core, and it takes approximately 1,150 Earth days to complete one circuit. But the planet's current position is not where it spent most of its history. Modeling of the system's past strongly suggests that when V391 Pegasi was expanding into a red giant, the planet was at a significantly smaller orbital radius, close enough to be temporarily enveloped by the outermost, most rarefied layers of the expanding stellar atmosphere. Inside those tenuous outer layers, the planet was still largely intact. The density of material in the stellar envelope at that stage was far lower than even the most rarefied air in Earth's upper atmosphere. But drag was still present. The planet would have been losing speed, spiraling inward, heading toward the hotter and denser layers below. What saved it, if saved is the right word, was the timing. V391 Pegasi shed its outer envelope in a planetary nebula before the planet could reach the truly lethal depths. When the envelope dissipated, the planet found itself at a somewhat larger orbit than before, slightly altered but fundamentally intact. It had, in effect, survived immersion in the outer atmosphere of a dying star. What this means for V301 Pegasi b's current composition is unclear. Any previous atmosphere would have been scoured away by the encounter. Any volatile ices on or near its surface would have been vaporized. Whatever it was before, ice giant, gas giant, something else, it is something different now. And it continues to orbit the white remnant of the star that almost destroyed it, circling quietly in the dark at a distance from which the star would appear as little more than a pale, very hot point of light. Some of the most forbidding environments in the galaxy are found not around ordinary stars, but around their strangest descendants. Neutron stars, the compressed remnants of massive stellar explosions, are among the densest objects known, packing the mass of the Sun into a sphere roughly 20 kilometers across. Many of them rotate at extraordinary speeds, emitting beams of electromagnetic radiation that sweep the sky like lighthouses. These are pulsars, and the regularity of their pulses makes them among the most precise natural clocks in the universe. This regularity is also what makes them useful for detecting planets. A planet orbiting a pulsar will periodically pull the neutron star slightly toward and away from Earth, causing the arrival times of its pulses to shift by tiny but measurable amounts. It was this method that led in the early 1990s to the discovery of the first confirmed exoplanets around any star. Objects orbiting a pulsar designated PSR 12057 plus 12 located about 2,300 light-years from Earth. Around 4,000 light-years away, another pulsar has a remarkable planetary companion. The neutron star at the center of this system rotates at roughly 10,000 revolutions per minute, emitting intense pulses of electromagnetic radiation with every turn. The planet orbiting it sits at a distance of only about 600,000 kilometers closer than the Sun's own radius. Its orbital period is 2 hours. This world is unlike anything in our solar system. Its mass is approximately 333 times that of Earth, and its radius is 4 times as large, placing it somewhere between a super-Earth and a mini-Neptune in physical scale. The surface gravity is roughly 20 times stronger than Earth's. Its average density is estimated at about 23 grams per cubic centimeter, significantly denser than any common mineral or metal found naturally on Earth. The leading explanation is that this planet is composed primarily of crystallized carbon under immense pressure. In other words, a world largely made of diamond compressed into its current form by billions of years of extreme internal pressure. The surface of this planet is continuously bathed in lethal radiation from the spinning neutron star overhead. There is no known mechanism by which any chemistry leading toward life could operate here. The question of how the planet came to exist at all is itself unresolved. The standard explanation is that it is not a planet in the conventional sense, not a world that formed alongside its star from a protoplanetary disk, but rather a remnant of a former binary companion, a once normal star that was gradually consumed by the pulsar over millions of years, until only a dense, inert core remained. Classified formally as a planet by virtue of its mass, it occupies a category somewhere between stellar remnant and world. Beyond the nearest stars, beyond the exotic planets and the pulsars, the galaxy becomes home to something darker and more extreme. Objects where gravity has overwhelmed all other physical forces. Black holes are not merely dense stars, they are points of no return, regions of space-time where the curvature becomes so extreme that not even light can escape. One of the closest known black holes to Earth lies approximately 3,300 light-years away in the constellation Monoceros. The object, designated A06200, is also catalogued as V616, and it is part of a binary system. Its companion is an orange dwarf star with roughly half the mass of the Sun. Every 7.75 hours, this companion star completes an orbit around something it cannot see, something whose estimated mass is approximately 6.6 times that of the Sun. A neutron star of that mass would be impossible. The upper limit for neutron star mass is well below this figure. The invisible object must therefore be a black hole. And while it cannot be directly observed, its presence makes itself felt in a dramatic way. The gravity of the black hole stretches and deforms its companion star, drawing material from the orange dwarf's outer layers and pulling it into a spiraling accretion disk. These disks, superheated by compression and friction, radius intensely across multiple wavelengths. It was the brightness of this accretion disk that first revealed the system's existence in 1917, when it temporarily brightened dramatically enough to be noticed on photographic plates. Around the V6-160 system, at least several dozen other stars are known to exist within detectable range, some of which likely have planets of their own. In time and in galactic terms, time is abundant. Some of those stars will drift close enough to the black hole to be pulled into its gravitational influence. When a star approaches a black hole too closely, the difference in gravitational force between the near side and the far side becomes overwhelming. Tidal forces stretch the star, first distorting it into an elongated shape, then drawing streams of material from its surface into the accretion disk. At sufficiently close range, a star can be torn apart entirely, its material spreading into a ring of superheated gas that spirals inward across thousands of years before crossing the event horizon and disappearing from the observable universe. The physics of a black hole's interaction with nearby matter is determined primarily by mass ratio and distance. Small, distant objects may orbit stably around a black hole indefinitely. Larger or closer objects experience increasingly powerful tidal disruption. And the question of whether planets can exist around black holes, a question that sounds almost absurd, turns out to have a serious answer. They can. 3 mechanisms have been proposed. First, in the aftermath of a supernova that creates a black hole, the remaining disk of gas and dust can condense under gravity, form clumps, and eventually produce rocky or icy worlds that orbit the compact remnant. The accretion disk's radiation might even be energetic enough to warm these worlds and melt ice on their surfaces. Second, when a black hole captures and destroys an existing planetary system, some of the surviving planets may be deflected into stable orbits around their new host. The encounter would dramatically transform these worlds, stripping atmospheres, melting surfaces, altering compositions, but the bodies could remain intact. Third, rogue planets drifting through the galaxy without any parent star occasionally come close enough to a black hole to be gravitationally captured and settle into stable orbits. None of these hypothetical systems have yet been confirmed in observation, but there is no physical reason to rule them out. In the far future, such systems may be more common than they are today as the galaxy's stars slowly exhaust themselves and leave behind increasing numbers of dense remnants around which the rubble of former planetary systems continues to orbit. Black holes are not a single type of object. They vary enormously in scale, and astronomers generally recognize 3 broad categories. The first and most familiar type forms at the end of a massive star's life cycle. When a star with at least 18 to 20 times the mass of the Sun collapses in a supernova, the resulting core compression can be so extreme that ordinary matter is overwhelmed entirely, and a stellar mass black hole is formed. These objects typically have masses ranging from a few to a few dozen times that of the Sun. They are not particularly rare. Estimates place the number of stellar mass black holes in the Milky Way at approximately 100 million, but their darkness makes them difficult to detect individually, and most are known only indirectly through their effects on nearby companions. The second category comprises the supermassive black holes found at the centers of most large galaxies. These objects have masses ranging from hundreds of thousands to tens of billions of times the mass of the Sun. Their formation mechanism is not entirely clear. They may have grown from stellar mass seeds by consuming gas and other stars over cosmic time. They may have formed through the direct collapse of enormous gas clouds in the early universe. They may have grown from the mergers of intermediate mass black holes, a category that is itself still being characterized. Whatever their origin, supermassive black holes are a defining feature of galaxies, and their presence shapes the evolution of their host structures in ways that are still being worked out. The third category, Primordial black holes exists only as a theoretical prediction. In the earliest moments after the Big Bang, when the universe was densely packed and its matter distribution was not perfectly uniform, fluctuations in density may have been large enough in some regions to cause direct gravitational collapse without any star formation being involved. The resulting objects would have formed with a wide range of masses from microscopic to very large. Primordial black holes with masses around 1 trillion kilograms would, by theoretical prediction, be evaporating today, releasing their final energy in an intense burst of radiation. No such burst has been detected, which places constraints on how many such objects can exist, but does not definitively rule them out. Detecting black holes requires inference. When a stellar mass black hole has a companion star, the anomalous motion of that companion reveals the unseen mass. The characteristic spectrum of material heated in an accretion disk can be identified in telescope observations. In some cases, a disk viewed from the right angle shows a dark central region, a silhouette of the event horizon against a glowing background. Gravitational microlensing, which occurs when a massive compact object passes between Earth and a distant star, produces a distinctive brightening and spectral shift that can be detected and analyzed. And gravitational waves, ripples in spacetime generated when two black holes spiral together and merge, have now been detected directly by instruments sensitive enough to register distortions smaller than the diameter of an atomic nucleus. The physics of a black hole's interaction with nearby matter is determined primarily by mass ratio and distance. Small distant objects may orbit stably around a black hole indefinitely, experiencing its gravity as they would any other massive body of the same mass. Larger or closer objects experience increasingly powerful tidal disruption. The key quantity is not the total gravitational force, but the difference in gravitational force between the near side and the far side of the object being pulled, the tidal force. As an infalling object approaches the event horizon, these tidal forces become enormous. For a stellar mass black hole, the tidal forces at the event horizon are extreme enough to destroy any normal matter long before it crosses the boundary. For a supermassive black hole, paradoxically, the situation is different. The tidal forces at the event horizon are relatively gentle, and an infalling object or astronaut hypothetically might cross the event horizon without experiencing anything locally dramatic. Only later, as the object approaches the central singularity, would the tidal forces become lethal. This asymmetry between stellar and supermassive black holes is one of the many counterintuitive features of general relativistic gravity. The question of whether planets can exist around black holes, a question that sounds almost absurd, turns out to have a serious answer. They can. 3 mechanisms have been proposed. First, in the aftermath of a supernova that creates a black hole, the remaining disk of gas and dust can condense under gravity, form clumps, and eventually produce rocky or icy worlds that orbit the compact remnant. The accretion disk's radiation might even be energetic enough to warm these worlds and melt ice on their surfaces. Second, when a black hole captures and destroys an existing planetary system, some of the surviving planets may be deflected into stable orbits around their new host. The encounter would dramatically transform these worlds, stripping atmospheres, melting surfaces, altering compositions, but the bodies could remain intact. An ice giant close to the disruption zone might be transformed into an ocean world, as its outer volatile layers are driven off. A gas giant might lose all its hydrogen and helium and be reduced to a dense stonian planet, a bare, rocky core. Third, rogue planets, drifting through the galaxy without any parent star, occasionally come close enough to a black hole to be gravitationally captured and settle into stable orbits. None of these hypothetical systems have yet been confirmed in observation. But there is no physical reason to rule them out. A planet orbiting a black hole would not be drawn relentlessly inward any more than Earth is drawn relentlessly into the sun. Orbital mechanics works the same regardless of what the central object is, so long as the orbit keeps the planet safely outside the region where tidal disruption begins. If, on the other hand, a planet strays too close to a sufficiently massive black hole, the sequence of events is unambiguous. First, the accretion disk radiation begins to heat and erode the atmosphere. Then, the orbital path tightens due to friction and momentum loss as the planet grazes the disk's outer material. Then, tidal forces begin to deform the body itself, stretching it toward the black hole's center of mass. At some threshold, this becomes irreversible. The planet is pulled apart into a stream of debris that spirals into the disk, heats to millions of Kelvin, and radiates briefly before vanishing across the event horizon. Nothing of the original structure survives. In effect, the planet becomes part of the black hole. Black holes are not a single type of object. They vary enormously in scale, and astronomers generally recognize three broad categories. The first and most familiar type forms at the end of a massive star's life cycle. When a star with at least 18 to 20 times the mass of the Sun collapses in a supernova, the resulting core compression can be so extreme that ordinary matter is overwhelmed entirely and a stellar mass black hole is formed. These objects typically have masses ranging from a few to a few dozen times that of the Sun. They are not particularly rare. Estimates place the number of stellar mass black holes in the Milky Way at approximately 100 million. But their darkness makes them difficult to detect individually, and most are known only indirectly through their effects on nearby companions. Stellar mass black holes grow by consuming gas from a nearby companion star, or by accreting interstellar material over millions of years, or by merging with another compact object. They can increase their mass substantially. When two stellar mass black holes spiral together and merge, they generate gravitational waves, ripples in the fabric of space-time that propagate outward at the speed of light, distorting the geometry of space as they pass. These waves carry energy away from the merging pair, causing them to spiral inward faster and faster until the final merger. The detection of gravitational waves by the LIGO and Virgo observatories beginning in 2015 opened an entirely new window on these events. Each detected merger provides a precise measurement of the masses of the two progenitor black holes and the mass of the final remnant, along with information about the direction and distance of the event. Dozens of such mergers have now been recorded. The second category comprises the supermassive black holes found at the centers of most large galaxies. These objects have masses ranging from hundreds of thousands to tens of billions of times the mass of the Sun. Their formation mechanism is not entirely clear. They may have grown from stellar mass seeds by consuming gas and other stars over cosmic time. They may have formed through the direct collapse of enormous gas clouds in the early universe. They may have grown from the mergers of intermediate mass black holes, a category that is itself still being characterized. Whatever their origin, supermassive black holes are a defining feature of galaxies, and their presence shapes the evolution of their host structures in ways that are still being worked out. When a supermassive black hole is actively consuming material, the surrounding accretion disk can outshine the combined light of every star in its host galaxy. From across the universe, these objects, known as quasars, appear as point sources of extraordinary luminosity, visible at redshifts corresponding to billions of light years of distance. The most luminous quasars outshine ordinary galaxies by factors of hundreds. For a brief period in the early universe, before much of their available gas was consumed, many galaxies were quasars. The Milky Way's own central black hole, Sagittarius A, is currently dormant. Its accretion rate is low and it generates only a faint glow compared to what it must have produced in earlier epochs of the galaxy's history. Evidence exists in the structure of the galaxy's halo and in the orbits of nearby stars that something dramatic happened at the galactic center billions of years ago. The current quiet is merely a phase. The third category, primordial black holes, exists only as a theoretical prediction. In the earliest moments after the Big Bang, when the universe was densely packed and its matter distribution was not perfectly uniform, fluctuations in density may have been large enough in some regions to cause direct gravitational collapse without any star formation being involved. The resulting objects would have formed with a wide range of masses, from microscopic to very large. Small primordial black holes lose mass over time through a process known as Hawking radiation, a quantum mechanical effect in which pairs of virtual particles near the event horizon result in a net outflow of energy from the black hole. For very small black holes, this process is fast enough to matter. Primordial black holes with masses around 1 trillion kilograms would, by theoretical prediction, be evaporating today, releasing their final energy in an intense burst of radiation. No such burst has been detected, which places constraints on how many such objects can exist, but does not definitively rule them out. A fourth, still more speculative category is the quantum black hole, a microscopic object that might theoretically form in high-energy particle collisions if additional spatial dimensions exist beyond the familiar three. The conditions required for this to happen cannot currently be achieved even with the world's most powerful particle accelerators. The predicted lifetime of such an object would be so short, far below what any instrument can currently resolve, that detecting one directly would require entirely new technology. For now, quantum black holes belong to theoretical physics rather than observational astronomy. Detecting black holes requires inference. When a stellar mass black hole has a companion star, the anomalous motion of that companion reveals the unseen mass, the characteristic spectrum of material heated in an accretion disk, broad emission lines, X-ray excesses, time-varying brightness, can be identified in telescope observations. In some cases, a disk viewed from the right angle shows a dark central region, a silhouette of the event horizon against the glowing background, as seen in the published images of M87 Fifth in 2019 and Sagittarius A in 2022. Gravitational microlensing, which occurs when a massive compact object passes between Earth and a distant star, produces a distinctive brightening and spectral shift that can be detected and analyzed with sufficient monitoring cadence. And gravitational waves have now been detected directly by instruments sensitive enough to register distortions in space-time smaller than the diameter of an atomic nucleus. The aggregate picture suggests a galaxy with approximately 100 million black holes distributed through its volume, drifting, accreting, occasionally merging, mostly invisible. The majority will never be individually detected. They will continue their silent work of collecting the matter that comes too close, changing the trajectories of stars that pass within their influence, and gradually over timescales beyond any human frame of reference, growing larger. The universe assigns no urgency to this process. Beyond all these stars, all these worlds, all these remnants and dark objects, the galaxy itself awaits. And to understand where we live, we need to pull back far enough to see the whole. The idea that the faint band of light crossing the night sky was actually a structure containing our own sun and billions of other stars was not always obvious. For most of human history, this pale arc was simply a feature of the sky named, imagined, mythologized, but not understood. The first person to systematically argue that the stars form a flattened disk-like distribution and that some of the nebulous patches in the sky might be separate, distant systems of stars, distant galaxies, was Immanuel Kant, writing in 1755. His reasoning was largely correct, but the instrumental capability to verify it would not exist for another century and a half. In the early 20th century, advances in telescope technology and photographic techniques allowed astronomers to measure the distances to variable stars in other galaxies and confirm that these objects were not nebulae within the Milky Way, but entirely separate systems, each containing billions of stars, some of them comparable to our own galaxy in scale. By 1936, Edwin Hubble had devised a classification system for galaxy types that is still in use today. Under this system, the Milky Way is a barred spiral galaxy, a rotating disk of stars, gas and dust, with a central elongated concentration of stars forming a bar from which two or more spiral arms extend. The Milky Way is a large galaxy by most measures. Its disk spans approximately 200,000 light-years in diameter. Its stellar population includes at least 200 billion stars, along with tens of billions of brown dwarfs, objects too low in mass to ignite sustained nuclear fusion, but too massive to be considered conventional planets. The number of planets in the Milky Way exceeds 1 trillion, and this is likely a conservative estimate. In addition, the galaxy contains vast quantities of interstellar gas and dust organized into clouds that range in size from a few light-years to hundreds of light-years across. All of this visible matter, however, represents only a small fraction of the Milky Way's total mass. Roughly 90% of the galaxy's mass exists in a form that does not emit, absorb, or reflect electromagnetic radiation in any detectable way. This is dark matter, and its presence is inferred entirely from its gravitational effects. The stars in the outer regions of the galaxy rotate around the galactic center faster than they should if only visible matter were present. Something massive and invisible must be distributed throughout the galaxy, providing the gravitational scaffolding that holds everything together. The total mass of the Milky Way, including its dark matter content, is estimated between 0.8 and 1.5 trillion solar masses. At the center of the Milky Way, shielded from direct optical observation by massive clouds of gas and dust, lies the galaxy's supermassive black hole. Designated Sagittarius A, it has a mass of 4.3 million solar masses. Its radius is less than 16 million kilometers, smaller than Mercury's orbit around our Sun. Despite this compactness, it is surrounded by an accretion disk extending approximately 3 light-years outward. And within just a few light-years of its event horizon, more than 6,000 individual stars have been detected. Some of these stars orbit at extraordinary speeds. One, designated S62, approaches the black hole to within 17.8 astronomical units on its closest pass, moving at 6.7% of the speed of light. At these velocities, the predictions of general relativity become essential for accurately describing the orbit. The axis of S62's elliptical orbit shifts by 75 arc-minutes with every completed circuit, a direct consequence of the curvature of space-time in the vicinity of the black hole. The first direct image of Sagittarius A was released on May 12, 2022, produced by the Event Horizon Telescope, a global network of radio observatories operating together as a single instrument. The image confirmed what decades of indirect evidence had already suggested: a compact, extremely massive object at the heart of the Milky Way, surrounded by a glowing ring of heated plasma. Its reality, which had been inferred through patient observation and calculation, was at last visually confirmed. Around 200 light-years from the galactic center, a second massive concentration of matter may be present, an intermediate mass black hole with a mass perhaps 100,000 times that of the Sun. If confirmed, this object would represent a category of black hole between stellar mass and supermassive that is currently the least well characterized of the three. Moving outward from the galactic center, one passes through the central molecular zone, an irregularly shaped region between 1,600 and 1,900 light-years across, with a total mass exceeding 60 million solar masses. This zone is dense with star-forming regions, gas clouds, newly forming protostars, and the remnants of stars that have already died in supernova explosions. The temperature within the zone varies widely, from 50 Kelvin in the densest molecular clouds to 600 Kelvin in regions heated by nearby stellar activity. Spectroscopic analysis reveals a complex chemistry within these clouds: carbon monoxide, methanol, hydrogen cyanide, and traces of more complex organic molecules. Surrounding the central zone is the galactic bulge, a roughly ellipsoidal concentration of older stars, tens of thousands of light years in extent, with a total stellar mass approximately 10 billion times that of the Sun. The number of individual stars within the bulge cannot be counted directly, because at its densities, the light from individual stars blends into a continuous glow. The bulge transitions smoothly into the galactic bar, an elongated, roughly linear structure approximately 13,000 light-years in length, which forms the central spine from which the spiral arms extend. At one end of this bar lies the star cluster Stephenson 2, within which astronomers have identified one of the physically largest known stars in the galaxy, designated Stephenson 2T18. Its radius is 2,150 times that of the Sun. If placed at the center of our solar system, its surface would extend beyond the orbit of Saturn. The star's extreme size makes it a hypergiant, an object in a transitional and unstable phase of evolution, consuming its fuel at an enormous rate and expected to end its life in a spectacular explosion within an astronomically short time. No planets are expected to survive in its vicinity. The central region of the Milky Way is densely populated, but this density is not conducive to life. Stars in the central kiloparsecs are closely packed, and their gravitational influence on one another's planetary systems would be disruptive. The intense radiation environment near the galactic center, from powerful X-ray and gamma-ray sources, from the accretion disk of Sagittarius AF, from the supernovae that detonate with much higher frequency in this region, would pose a severe hazard to complex chemistry, let alone to the kind of biochemistry that might support life as we understand it. Astronomers have defined a concept called the galactic habitable zone, a ring-shaped region of the galactic disk, centered roughly between 22,000 and 29,000 light-years from the galactic center, where conditions are thought to be most favorable for the emergence of biological life. Within this zone, star systems contain enough heavy elements which only form inside stars and are released into interstellar space by supernovae to build rocky planets. They are also far enough from the dense, radiation-intense central region to avoid lethal exposure. Beyond the outer boundary of the zone, the abundance of heavy elements drops off to levels where planet formation becomes difficult. The solar system lies at approximately 27,000 light-years from the galactic center, well within this hypothetical zone of habitability. This placement may not be coincidental. Whether it is common, rare, or somewhere in between to occupy such a position remains a question at the frontier of current research. Stars are known to migrate significantly within the galaxy over the course of billions of years, and a star system that begins its life inside the habitable zone may drift outward or inward over time, just as a system that forms outside the zone might later drift into it. The body of the Milky Way's disk is conventionally divided into two layers with distinct properties. The thin disk, extending roughly 1,000 to 1,300 light-years in thickness and 100,000 light-years in radius, contains approximately 80% of the galaxy's visible stellar mass. It is the most recently formed major structural component of the galaxy, and it contains most of the gas and dust from which new stars are still being born today. The thick disk shares a similar lateral extent, but is 4 times as thick and far less dense in its stellar population. It is composed predominantly of older stars and contains very little interstellar gas, making it an inactive region in terms of ongoing star formation. The galaxy's current structure was not built in isolation. Evidence drawn from the motions and compositions of stars within the Milky Way suggests that between 8 and 11 billion years ago, the galaxy underwent a significant merger event, incorporating a smaller galaxy known as Gaia Enceladus into its own structure. This collision contributed several billion stars, large quantities of interstellar gas, and significant amounts of dark matter to the growing Milky Way. The turbulence of the merger is thought to have triggered an intense period of new star formation and to have contributed substantially to the formation of the thick disk. The spiral arms of the Milky Way are the galaxy's most visually striking structural elements when seen from outside. They are not static features, but rather regions of enhanced star density and star formation, waves of compression, moving through the galactic disk like ripples on a pond. The two primary arms, the Scutum Centauris arm and the Perseus arm, extend from opposite ends of the central bar. Two secondary arms, the Norma arm and the Sagittarius Carina arm, fill in the intermediate spaces. A fifth possible arm associated with the Cygnus region is sometimes identified in addition to these four. Within the spiral arms, the rate of star formation runs 3 to 5 times higher than in the interarm regions, because the density waves compress gas clouds to the point where gravitational collapse begins. Young, hot, massive stars form first blue-white giants that burn briefly and brilliantly before ending their lives as supernovae. These supernovae in turn compress the surrounding gas further, potentially triggering the next wave of star formation. After tens of millions of years, young stars disperse from the loose, open clusters in which they were born, spreading outward into the disk and adding to the galaxy's general stellar population. The solar system is located in a minor spur called the Orion Arm, a shorter structure linking the Sagittarius Carina Arm to the Perseus Arm, at a distance of about 27,000 light-years from the galactic center. From this vantage point, looking toward the galactic center, we see not the bright core itself, but the Great Rift, a dark lane stretching across the visible band of the Milky Way, formed by dense molecular clouds that absorb optical light. The Great Rift has a mass roughly 1 million times that of the Sun and contains complex chemistry, including hydrogen, ammonia, alcohols, and even simple amino acids detected through spectroscopic analysis. It is nearly opaque to visible light but transparent to radio waves and infrared radiation, which is how its contents can be mapped from Earth. The Great Rift represents a future stellar nursery, a reservoir of raw material waiting for the right conditions to collapse into new stars and planetary systems. The timeline for this process is measured in millions of years. For now, it hangs in the galactic plane as a dark seam across the Milky Way, the visible reminder that the space between stars is not empty. Beyond the disk, the Milky Way is surrounded by an enormous, sparsely populated structure called the halo. The visible portion of the halo extends approximately 260,000 light-years from the galactic center in all directions, forming a roughly spherical distribution. Despite its vast extent, the visible halo accounts for only a small percentage of the galaxy's total mass. Its most prominent inhabitants are globular clusters, tightly bound spherical groups of stars, typically containing hundreds of thousands of individual suns, many of them among the oldest objects in the universe. The stars in some of these clusters are more than 12 billion years old, predating the formation of the Sun by nearly 8 billion years. Alongside these globular clusters, the halo contains enormous stellar streams, rivers of stars that trace ancient gravitational interactions. The Sagittarius stream, one of the best studied examples, is composed of thousands of stars wrapping around the Milky Way in an elongated loop oriented nearly perpendicular to the galactic plane. These stars originated in a small companion galaxy, the Sagittarius Dwarf Elliptical Galaxy, which has been losing material to the Milky Way's gravitational influence for billions of years. The remnant galaxy currently lies some 500,000 light-years from the galactic center and will be fully absorbed into the Milky Way within several billion years. A smaller companion galaxy in the Canis Major direction has fared even worse. Largely disrupted by tidal forces, it has shed millions of its stars into an extended stream that has now wrapped 3 times around the Milky Way over its history. The combined mass of these stripped stars is approximately 100 million solar masses, like the Sagittarius stream. This structure is a record of cosmic cannibalism, the Milky Way growing through the gradual consumption of smaller neighbors, beyond the visible halo, extending to distances of perhaps 2 million light-years. An even larger dark structure is inferred to exist, the dark matter halo. This invisible envelope is detectable only through its gravitational influence on the motions of stars and satellite galaxies. It emits no electromagnetic radiation across any wavelengths. It does not interact with light in any way that can be observed. And yet it is thought to contain the majority of the Milky Way's total mass, sculpting the gravitational environment within which all the stars, gas, dust, and visible structure exist. The nature of dark matter, what it is made of, how it was produced in the early universe, whether it is a single type of particle or a complex mixture, remains one of the deepest unsolved problems in physics and astronomy. Decades of experiments have failed to directly detect dark matter particles. Theoretical frameworks exist, but none have been confirmed. The dark matter halo of the Milky Way, distributed through a volume hundreds of times larger than the visible galaxy, is the most immediate and unavoidable example of this mystery pressed right up against our daily reality. The Milky Way that exists today took 13 billion years to build. It began as a small cloud of hydrogen and helium, drawn together by gravity in the early universe, seeded with the gravitational scaffold of dark matter that had been present since near the beginning of cosmic time. Early generations of stars lived and died, forging heavier elements that enriched subsequent generations. Mergers with smaller galaxies added new stars and new gas. Spiral arms formed and dissolved and reformed. Stars came and went in their billions, each one a brief spark in a structure built to last far longer than any individual component within it. The Sun joined this structure only about 4.6 billion years ago, a late arrival, inheriting a galaxy already middle-aged in 4.5 billion more years. The Milky Way will collide and merge with the Andromeda Galaxy, producing a new combined structure whose shape and character astronomers can already begin to model, but whose specific details remain unpredictable. The galaxy we live in today is not the final form of anything. It is one frame in a very long film. Every question answered about the Milky Way opens several more. The nature of dark matter, the origin of the first stars, the mechanism of galaxy formation, the question of whether intelligent life exists elsewhere in the 100 billion or more star systems contained within our galactic disk. These are not questions at the margins of science. They are its center, the problems around which some of the most sophisticated instruments and sharpest minds of our time are organized. We began this journey in the neighborhood of our own star, 4 light-years, the nearest neighbor, already a practically unreachable distance given current technology. We end it 2 million light-years out at the edge of the dark halo. Looking back at a structure so large, it takes light longer to cross than the current age of the universe would have allowed when the galaxy's first stars were being born. Everything we have seen, the stars, the worlds, the black holes, the dust, the dark matter, is part of a single system. Our Sun is one of its 200 billion components. Earth is one of its trillion or more planets, and we are, as far as we currently know, among the only beings anywhere within its 200,000 light-year span who have looked up, asked why, and begun to find out. The universe, it turns out, does not keep its secrets easily, but it does keep them long.